All right. All right, so we're gonna pick up where we left off. You can't see can you see my screen?
I can see it, Shauna.
All right, so we left off, you said on 24. So we were talking about distribution shape yesterday. Skewness, which is how much less or more than normal you are. So normal is bell-shaped, skewed is favoring one side or the other. And we kind of went over that. We went over some z-scores a little bit. We said that z-scores represent the number of standard deviations you are from the mean. If your z-score is 0, you're at the mean. If your z-score is positive, you're above the mean. And if your z-score is negative, you're below the mean. Are you with me?
Yes, I'm with you.
Frozen. Okay, I was like, is he frozen? All right, then we left off here with Chebyshev's theorem. And this, what I was telling you about this is it's related to the empirical rule, in that the empirical rule describes normal bell-shaped distributions. Chebyshev's theorem is more conservative, and you can use it to describe any distribution of any shape. It'll give you and this is kind of what's nice. She pre-computed some of the proportions down here. So this is important. This is slide 15. If she tells you, like, we have a question about what something like between what interval does 75% of the data lie, she pre-computed some of the proportions for you. So we saw 2 yesterday. She computed 3 here, 4 and 5 for you. It doesn't have to be an integer. You could be 75.6%, and then you would have to recompute what K is. But you just recompute it by putting the percentage into the formula for P and manipulating it to find what K is. So let me just show you that so that because that's something that students struggle with. So let me show you that really quick. So remember the formula here. The formula is, I'm going to use equals. It's really greater than or equal to, but for our purposes here, I'm going to use equal for now. P equals, and I'm going to get rid of caps lock. P, all right, there we go. No, that's not what I want to do. Okay. P equals 1 minus 1 over, and I'm going to put the underneath here so it's a little easier to read it. This is K squared. All right. So then basically what this says is that this is 1 minus 1 over K squared. So then where K is greater than 1. Okay, obviously, because if K equals 1, then the percentage is 0. So the formula doesn't work for K equals 1. So suppose that we would like to know the minimum percentage of data that lies within, let's say, 2.5 standard deviations of the mean. In other words, what this says is that what this means in English is that we want to find, in other words, find P, find the percentage when K is 2.5. Okay, that's what that means, within 2.5 standard deviations of the mean. All right. So in this case, all you're going to do is the easiest thing to do, you could do some fractions and manipulate this and do the arithmetic, but your calculator will do it for you. So, let your calculator do the hard work. We believe you can do arithmetic. 1. So we have P equals 1 minus 1 over 2.5 squared. Now remember, you want to square not the whole fraction, just the 2.5. So here you get that. Now I'm gonna stop sharing for a minute and put up the calculator screen.
Okay.
So we can see that. So there we go. And I'm going to clear this out and I'm going to share the screen here. So now we're going to share this part of the screen. And we have 1 minus 1 over. And at the bottom, you want to make sure you put parentheses 2.5. It's squared. So you're going to square this. And we hit enter. And that gives me 0.84.
Right.
So about 84% of the data, no matter what kind of, a minimum of 84%. Now, depending on the type of distribution you have, this could be more, right? In a normal distribution, this is about 95, 96%, something like that, right? But in a uniform distribution, it could be less. In a skewed distribution, depending on which way, it could be smaller. This is the minimum percentage, 84%. Now, the other way they can ask a question, and I think we did this yesterday. The other thing they can ask you to do is, instead of doing this calculation, which we said was equal to the percentage here, just to finish this answer, the percentage is about 84%. Now, the other thing they can ask you, because they can do intervals, they can do a lot of things, but the other thing they can do with this formula is sometimes they give you the percent and they say something like, they'll ask you a question like I asked you yesterday. They'll say something like, between what interval does so many percent of the data lie, right? And in that case, before you can find the interval, you have to find the percentage. So they might say, suppose that, I'll just make this up. IQ scores have a mean of 100 with a standard deviation of 15. And for the sake of this problem, I'm going to say assume that the shape is not known. The shape of the distribution is not known. All right. So I can say, let's do something like this. I can say, how many, okay, within, so I'm going to ask you 2 questions here. I'm going to say, first question is, within how many standard deviations would you expect 65% of the data to lie? Within how many standard deviations of the mean would you expect 65% of the data to lie? In other words, what we want to do here is we want to find K when P is 0.65. That's essentially what we want to do, okay? So in this case, you would do 0.65 is equal to 1 minus 1 over K squared. And you can do this with a calculator. It's a little bit more, you can use the capacity of the calculator to do this, but it's not too hard to do this manually either. What you can do is, if I were going to solve this equation for K, I'd start by subtracting 1, this one here, the first one, from each side, right? So I'd have something like this. I'd have 0.65 is equal to, minus 0.65 minus 1 is equal to negative 1 over K squared. Now, both sides of that are negative, but we're going to fix that in a second. So if you do this part, you get 0.65 minus 1 is a negative 0.35.
So when we do the left side, we got to do the right.
Yeah, but when I subtracted 1 here, I'm subtracting 1 from each side of the equation, right? So if I subtract 1 from here, I'm doing 1 minus 1. So this one, in other words, this 1 is going to drop out.
Okay.
Right? So I end up with negative 1 over K squared. Questions about this?
No, I'm with you.
Now, I have negatives on both sides. So it's not going to change it. What I'm going to do here is this technically is a proportion right now, right? So what I'm going to do is I have negatives on both sides. So if I multiply both sides by -1, I end up with positive numbers. And I get 1 over K squared, right? Now, solving for K, it depends on how you feel comfortable doing it. This 1 over K squared is a fraction. So I'm going to multiply both sides by K squared to get rid of the fraction, right? So I have 0.35 K squared is equal to 1. Are you okay here?
I'm okay.
Now from here, we're going to continue on the next screen. So we have, let me write it again here, 0.35 K squared is equal to 1, right? Now I'm going to divide by 0.35 on both sides. So I'm going to have, it's going to look something like this. 0.35. And here I have 0.35. So now this is going to give me k squared on the left is equal to 1 divided by 0.35. Now, if I put in that in my calculator, let me share the screen. So I have 1 divided by 0.35. What do you get for your answer?
1 divided by 0.35. I get 2.86.
Yeah, roughly, yeah, 2.857, 2.86. That's fine. So now this is k squared is about 2.86, right?
Mhm.
Now that's k squared. That's not k.
Now
So
you gotta square it.
I'm going to take the square root of it. So k is the square root of, I'm going to write it like this, square root of 2.86. And so k here, if I go back to the calculator and just take, I can either use, just for the sake of comparison, I'm going to do it with the actual number first, and then I'll do it with our approximation. So if I did that's going to be about 1.69 if I use the actual number itself. If I use 2.86, then I get 1, yeah, so it's roughly the same. Sometimes it's a little different. But my point here is that if you're 1.69 standard deviations away from the mean, so k here would be, k here would be 1.69. So what this means is that, so 65%, a minimum, so a minimum of 65% of the data would be within 1.69 standard deviations from the mean. Okay. Now I could go and figure out what that interval is. It would require some mathematics, but this would be my K. It wouldn't be my IQ score, right? But I could, if I wanted to know B, if I wanted to know between, or how about within what interval of IQ scores would a minimum of 65% of the data fall, right? So we figured out what K is, right? But now I want to know what that IQ score would be, right? Well, remember we said, let's recall, because that was a couple of screens ago. So let's recall this. We have a mean, recall that the mean is 100 mean is 100, and the standard deviation is 15, right? So if that's the case, we're looking at 1.69 standard deviations from the mean, all right?
Okay.
So we're gonna take the score is gonna be, so the lower limit, the lower part of my interval would be 100, the mean, minus, because I'm below the mean, right? Minus 1.69 times my standard deviation, which is 15. Now, the reason I wanted to go back over another example like this is to show you the difference between K and S. K and S, right? K is this 1.69, right? That corresponds to my 65% of the data. S here is the standard deviation of the scores that I'm using. All right, my upper boundary, my upper would be 100 plus 1.69 times 15. Questions about this?
No, Shauna, I think I got you.
So now I'm just going to do those calculations for completeness. So we're going to go ahead, put it up here. So this is 100 minus 1.69 times, oops, 1. Although put it in your calculator correctly or you won't get the right number. Because that's important. 15 here.
74.65.
Looks like it to me, yes. And then here I'm going to go ahead and do it for the plus, the big one. Now should be more than 100.
125.35.
It probably would be if I could get my cursor to move.
Uh-oh.
But it's frozen. So let me stop sharing and come back. See if that's, I don't know if it's something, there it is. It was frozen with the calculator. There we go. What I was wanting to do was put a plus here. Okay, well, fine. I'll just have to do it again. Entry. All right, so let's do this here. So this is a plus. So now, yeah, so it's between 74. If you round to the nearest point, which is probably the most legitimate thing, about 75 and 125. About that. About 75 and 125. Depending on, I mean, this is one of those cases where if they told you how many decimal places or whatever, then you would have, this would be approximately, this would be about 75. This would be about 75, and this would be about
125.
125. So that, this would be a different, this is a different number than you would get if it was normal by the empirical rule. But I just wanted to show you that. So whenever they ask you for an interval, because sometimes they will, like an interval of however many, you have to know what K is first. Now, if they give you one of the percentages that's on your slide, if they give you one of the percentages, then by all means, use it. You know what I mean? If they tell you what percentage of the data lies, what what portion of the data lies within 75%? Well, you know K is 2. So, or in this case, Z, because she changed it to Z. But,
Okay.
and I didn't notice that, but this is Z, but it's the same formula. Then you can go and you know what K is, you know what the percentage is, so you could go for the interval in that case. And then she reiterates it for you here. 75% lie within 2 standard deviations, 89 lie within 3, and 94 lie within 3. Okay. Now, here she gives you an example. What percentage of the values will fall between 10 and 26 for a data set with a mean of 18 and a standard deviation of 2, right? Well, you have to look at what this picture looks like. Okay, now I'm going to give you a little, I don't know if she gave you this formula, but basically you want to know what K is, right? So what you can do is you want to, basically it's kind of like doing the Z-score. If you look at your drawing, it will kind of help you, all right? So you have 10 on this side, you have 10 here. You have 26 over here. So this time they gave us the interval, right? They said, here's my interval, right? And this time they want us to find the percentage. I took it the other way. But here's my interval, 10 and 26, with a mean of 18. So the mean's here, 18. And you want to figure out, now she wants to know the percent, right? But before you can find the percent, you need K, don't you?
Right.
Now, there's a couple of ways to do this. And looking at the picture, it's a little bit more intuitive, I think. You can either do the distance from 10 to 18, right? Or you can do the distance from 26 to 18, right? Because remember, we're talking about the distance on either side of the mean, and the mean is 18. So if you want to find K, K is going to equal, K is going to equal either, I'm going to use the upper limit of the interval minus the mean divided by the standard deviation. You can also use the lower limit if you want, but it would look slightly different. So here you get K is equal to, if I use the upper limit, I have 26 minus 18, and I'm dividing it by, what's the deviation? By 2. Sorry, I was having a brain freeze. By 2, right? Because she tells us that the standard deviation is 2. So now you have 26 minus 18 is 8. 8 divided by 2 is 4, right? 8 divided by 2 is 4. So K is 4, right? Now, what percentage would that be? Well, you can put it back in the formula, or you can go back up to the slide, because this was one of the numbers that she gave you. when you have z equal to 4, and I used k, I have that bad habit. She's using z, but
Okay.
this is 94% because she's already calculated it. Okay. Now, how would you get that if she hadn't calculated it? You would just you would come over here and you would use your little trusty formula with k equal to 4. The percentage is greater than or equal to, right? 1 minus 1 over 4 squared. Remember, you're only squaring the 4, not the fraction, not the whole fraction. So if you do this calculation, 1 minus 1 over 4 squared, you'll get about 94. Questions here?
No, good, Shauna. Thank you.
So that's how that works. And I find that sometimes when students are learning it, if they draw this out, it helps. You don't have to. It doesn't change the problem solving in any way, but sometimes it helps to be able to visualize it. Okay. Just be careful about thinking that this is normal, because it's not. But the reason you're putting the mean in the middle like this is because you need to figure out how far you are from either side of the interval. And they have to be the same. You have to be the same distance from the left side of the interval as you are from the right. So in that sense, the mean is in the middle of the interval, but the distribution isn't necessarily normal. Okay.
Thank you, Shauna.
All righty. So that was that part. I think we've probably overkilled this part, but if you have questions about any of this now, you should.
I got some good notes here, Shauna. So what I'm going to do today, I got some time to go into the book and do some examples from there.
Yeah, and when they start asking you questions, you'll have a better. Okay, so the application of Chebyshev's theorem results in conservative bounds. The actual percentage may be much larger, okay? If we know that now this is the point that I was making yesterday, so I was ahead of her. If I were teaching it, I would have made this point first because the empirical distribution is more familiar to you probably. But basically she's saying, if our data are drawn from a relatively symmetric distribution, then we can make more precise statements by using the empirical rule, which is that picture that I showed you with the bell-shaped curve and the other percentages from yesterday. So she's going to cover that in more detail in chapter 6. And the empirical rule, here's those percentages. Those are on slide 20. Okay. Now she has those percentages to 2 decimal places. I've never memorized them to 2, but there they are. Just keep in mind, don't confuse them. Okay. These are percentages for the empirical rule. They apply to bell curves. The Chebyshev's theorem applies to any distribution, but it's much more conservative. So that's why those percentages are not the same. And here we have our bell curve, the one we were talking about yesterday. Okay.
Shauna, if I'm taking an exam, when will I know to apply Chebyshev's or empirical rule?
Okay, so if that's a good question, generally if they're asking you a question about that, it will say that. Or remember, if it's normal, this applies.
Oh, okay.
If it's normal or approximately normal, this applies. If you don't know what shape it is, or if they tell you, use Chebyshev's theorem 2, then you'll use Chebyshev's theorem and Chebyshev's percentage. Okay, so the good news about this is we covered this yesterday in some detail, and you're going to cover that in more detail in chapter 6, but we kind of talked about this already yesterday. Now, do you need me to go over the procedures for outliers or not?
Maybe quickly, Shauna, just to.
Okay, because it's a whole procedure. I can do it. I just wanted to know if you needed me to do it or not. So an outlier is an unusually small or an unusually large value that's in a data set.
Mhm.
Sometimes you kind of have some intuition about it. That, oh, that looks large, you know, but there's a procedure that you go through to see if it actually is an outlier or not. And so here, now she has a different criteria for outliers. The Blumen book, Blumen will use Z that's greater than 2 generally, or 2.5. This book seems to be using 3 as the percentage. Okay, so this has some bearing. If you look at Blumen will tell you that outliers are a Z-score that's greater than about 2.5, 2 to 2.5, depending on what situation you're doing. This book, she has 3 on her slide, so just be aware of that. Okay. But, and she goes through and she, again, these are the Z-scores. Okay, so she's doing it. This is a different procedure than the Blumen book has. The Blumen book has a whole procedure about you rank the data, you find the quartiles, you do all that. She doesn't do all that. What she does is she finds the Z-score for all of the data. She's talking about the apartment rent data. So she's talking about the data that's up here that she converted to Z-scores. Okay, so she did all those calculations all those times. Score minus, she did this calculation here on slide 13. She did this calculation for every single rent. Okay.
Okay.
And what she's doing is she's looking, here's my standard scores. Okay. Now my outliers are going to be the Z-scores that have an absolute value of 3 or more. So if you look at these Z-scores here, find the ones with really extreme Z-scores. Well, we see that we have a lot that are close to 2, don't we?
Yes, we do.
We have a couple down here that are 2.27, and she's saying that it's 3. So I would say that by your rule, you probably don't have any, but let's see what she says down here. Now she says, yeah, so here, if you notice, 2.27 occurs, right? Now for Blumen, this might be like a moderate outlier, these last 2.
Okay.
But for your book, it's not. So you don't have any outliers in the data, and you're using an absolute value of Z greater than 3 for your test. Okay. Questions about that?
No.
Okay. Now, 5-number summary and box plot. We taught, okay, here's the 5-number summary. Okay. The 5-number summary is always these 5 numbers in any distribution. Smallest, the minimum, the first quartile, the median or the second quartile, the third quartile, and the maximum. Okay. Those are always the 5-number summary. Never deviates from that. Now, we talked quite a bit about the 5-number summary already, and we talked about how to find, we talked a little bit about the box plot, right? In your other video yesterday. So the quartiles are the edges. So if you look here, she's created a box plot for you, right? At least part of the box plot. She hasn't finished it yet. But if you notice, where is our median here?
475.
Right, that's our median. What about our first quartile?
The 445 and the
something like that, yeah, and 530, 540 maybe. 525 actually, because it's right on the, so those are your edges, your quartiles, right? Now, do you think this is skewed a bit, this distribution?
Yes.
How do you know that?
It's not symmetrical.
Right, but how do you know by looking at the box plot that it's not symmetrical?
The median?
Right, if they were symmetrical, the median would be exactly in the middle
Mm-hmm.
of the box. This box plot is skewed left because the median is to the left of center of the box, okay? Now here, notice, she's showing you the whiskers, okay? So she's making the whiskers dashed, and your box plot looks like this. Now here she gives you another example with more data, okay? This is on slide 31.
Uh-huh.
And so you can go through and do all that. I'm not gonna, I think we've beaten this horse enough.
Especially because I can use the 1-bar stats for that, right, Shauna?
Yes, you can. Yes, you can.
Yeah, that's
And I mean, but you should know how to interpret the box plot if it's given to you.
Okay.
So now we've talked about measures of center, like the mean, the median, the mode, right? We've talked about measures of shape. I mean, we've talked about the shape a lot. Now we're going to talk about measures of association between two variables, okay? And so this is something that Blumen doesn't do a lot of. Blumen does covariance, but with one variable. That's why I was giving you the SX yesterday. That's one variable, but this is two. So covariance is a measure of the linear association between two variables. Positive values indicate a positive relationship. Negative values in okay. And here's the formula. There it is. This is the formula that I had to go look up the other day, trying to find it.
Mm-hmm.
So basically it's the score minus the mean of X, the score minus the mean of Y, multiply, add them together, then multiply them and divide by n minus 1.
Score minus mean of X over.
No, score minus mean of X
Uh-huh.
added together times score minus the mean of Y over n minus 1. So in other words, what you would have to do here would be you'd take every score of X, you'd subtract the mean of X. You'd take every Y score, subtract the mean of Y from it. Okay, add both of those groups, like your differences, add the differences together, multiply them, and then divide by n minus 1. Okay, and this is related to the correlation coefficient, which looks very similar to that. And here you have, this is the sum of xy divided by the sum of x times y, and if it's populations, it turns to sigma. So here, this gives you covariance and the correlation coefficient. Now, she has a tendency not to show you how she did it, but here she did a pretty good job. So this is one variable, the average driving distance with your golf club. And this is your score on the 18th hole. So what she does is your average driving distance is your X right here.
Right.
Your average golf club, your average score on that hole is your Y. Before she starts computing either the correlation coefficient or the covariance, either one, she finds the individual mean and the individual standard deviation of each group. Okay.
Mm-hmm.
So she finds the average of my driving distances, the average of the X column. Okay. Your calculator will do this for you. This is your X bar. and your Y bar respectively.
Okay.
It will do that for you. It will also give you the standard deviations there. Record those, okay? Now, what she doesn't show you here, she gives you the formula, but she doesn't show you where these came from. This third column, okay? What she's doing here for X is she's doing this. She's saying, okay, for let's say my first X, right? I have 277.6. So this is 2. Let me change colors because I mean it's hard to see. It's 277.6, right? And then you're going to subtract the mean of your X's, which is 267.0 minus 267.0. If you subtract it, you'll get 10.65 is what she gets. You'll get something, you'll get like 10.6 because she probably rounded these, but that's where she's getting it from. Okay, that's where it's coming from. The score minus the mean. The score minus the mean. So if you take 259.5 and you subtract 267.0, you should get negative 7.45. So if you were to take 259.5 and subtract the mean, which is 267, you should get negative 7.4. I think her average must be a little, what she wrote on the slide is a little off because these are not going to be exact, but that's where she got the numbers from. Okay.
Any way for us to do this calculation and enter the data in the
Yeah. Yeah. You can do that. You have to use columns, but you can do that. Yeah. So if you were to take, let me if you can't, yeah, I would highly suggest that. I don't think you should be doing it by hand, but I think it's instructive to know where they're coming from because she has a tendency not to put those in there. Right. And it's hard to follow if you're learning it, it's hard to follow where she got some of that from. It's well done, but I think she assumes that you can do that. You know what I mean? Mm-hmm. Anyway, so let me put this on the screen here. All right, so what I'm going to do is I'm going to go to stat. I'm going to go to stat. And I'm going to go to edit. And I'm going to clear my lists out because I need to be able to know where my data are. And I've got a ton of data in here. So let me do this like this. Second memory. So what I'm going to do is go ahead and I'm going to go to stat here. Go ahead and oh, I didn't. Second memory. Clear all this number 4. All right, so enter. There I go. Now if I go stat edit. Okay, go ahead and read me the numbers for X.
Yes, ma'am.
Please.
That would be the average driving distance, right? 27.
Right. 227 something.
It's 277.6. Oh,
277.6. Okay.
259.5.
259.5.
269.1.
269.1.
67.0.
267.0.
255.6.
255.6.
And the last one is 272.9.
Okay, so you put those, your X list is in L1. It's kind of like if we were doing a scatter plot. You're going to do your X list in L1. And then you're going to put your Y list in L2. And I'm going to scroll back up and come over here. 272.9 was our last one.
Yes.
Okay. Now, how about for our score on the whole? What do we have?
69.
Okay. What else?
71. 70.
Okay.
70.
Okay.
71. 69.
And 69. Okay. There's my data. Now, what I'm going to do here is I'm going to go up to, I'm going to have this do some calculating for me. Okay. But first, I'm going to run a stat calc and I'm going to write down some numbers. Okay.
Okay.
So what I'm going to do is this. I'm going to run a stat calc. I'm going to go stat, go to calc. Now you can do this with one var stats if you want, but to save a little time, you can do it with two variable stat.
Okay.
Because this is two variables, X and Y. If you go to two variable stat, you want to make sure that you enter your X list. So your X list here for me is L1. And my Y list is L2. I don't have a frequency list. So I'm going to calculate this. Now, the numbers that I want to pay attention to are the numbers that I see on the screen. And I've got this crazy enter search term. I'm not sure why that's in the way, but this is 266.95 is my X bar. So what I want to do is I want to write down my X bar. So I'm going to annotate here. I'm going to write down my X bar. My X bar is 266.90, right? And I want to write down my SX. Now, I don't know how many decimal places she used, but I'm going to write down my SX as 8.21918. 8.21918. The more you put in, the more accurate it's going to be. Now, you have more arrows down here. So what I'm going to do is I'm going to go to my mouse and I'm going to arrow down. And notice it does the same thing for Y. So it gives me my Y bar, right? My Y bar is 70, and I want to find my S sub Y. So I'm going to write those two numbers down. Y bar is 70. Okay. And my S of Y is 0.89443. Okay. So questions about that?
No, Shauna, I'm with you. I got the
Okay,
same.
now we notice that N is 6. We need that for later. We have 6 numbers. Okay, so what I'm going to do now is I'm going to begin to leverage my calculator a bit. So what I'm going to do is I'm going to go back to stat. I'm going to go to stat right here. I'm going to go into my edit screen. And you see how I'm in L3 right here? You see how I'm in L3? What I'm going to do is I'm going to push the up arrow key so that L3 is highlighted.
Okay.
And when I come down here to L3, you'll notice that L3 is blank. What I'm going to do now is I'm going to hit enter and my cursor is going to pop down to the bottom.
I see it.
Right? Now, what I want to do is in L3, what I'm going to create, I'm going to, first of all, I'm going to create a name. I could create a name for L3 if I want. I'm going to leave it as L3 right now, but I'm going to create a formula just like a spreadsheet does. Okay. And what I want L3 to be is X minus X bar. Okay. Because that's what she used. So what I'm going to do is I'm going to take, and what I want you to do is, this is what we're going to do. We want to take L1, the values in L1, and we want to subtract X bar. That's why I said it's easier if you write it down,
Okay.
right?
Okay.
And you can paste it in directly and import it, but that's more keystrokes. It's just easier to write down once and type in for me, you know? So I do, now to get L1, what I do is I go second, L1. Then I go and make sure you use the big minus, the minus sign, minus X bar. Now, X bar is the number you wrote, which is
266.90.
266.90. And if you put that in there as L3, L3 gets this formula. It will compute all of those values for you. So 11.6, negative 6.5, 3.1, 1, negative 10.4, and 6.9 is what I have here. Okay. Now you can have it do more decimal places or whatever, but that's how you do that. Okay. Now that's your X minus X bar, right? But we also need Y minus Y bar, if you remember. Okay. So we're going to go over here and we're going to say, okay, we're going to go to L4 and you can do that by arrowing over. Okay. I'll wait for you.
Okay, I'm with you, Shauna.
So we're going to go to L4 and we're going to do it for the Y's, which is L2 now. So we're going to hop the arrow up right here. Make sure L4 is highlighted. Hit enter. Okay. Make the cursor pop to the bottom. And then you're going to put in second L2 because you're doing Y this time. L2, which is the Y, minus Y bar, which is 70. And it's going to take 70 from every value in L2. And there we go. Okay. Now, this L3 column, this column that you see in the middle of my screen right now, is X minus X bar. And L4 is Y minus Y bar. Okay. So what we want to do now, we need to multiply those together, is what the formula says. So guess what? We're going to make another column over here.
All right.
L5. And we're going to multiply L3 by L4. Okay, L3 by L4. So I'm going to come up there, highlight L5, enter. And we're going to do L3, which is X minus X bar. times L4, which is y minus y bar, L4. Okay, I'm gonna multiply them, enter. There they are, okay.
Nice.
Now that's almost the formula, if you remember. We multiplied everything together. We got to add it up, right? So let me come back here for 1 minute before because this is a lot. It's a lot to process, okay? So we created this L3 column with L1 minus X bar, which we wrote down. We created L4 with Y, which was L2 minus Y bar, which we wrote down. And L5 was the product of these two. Now, depending on what I'm looking for, if I'm looking for the covariance, let me come back up here to this formula here. This says that you take the sum, that's this curly Q thing here.
Okay.
Take the sum of these products. Now, the product here, that's L5, because we multiplied it, remember? So basically, we want the sum of L5. Okay, so all I need now is the sum of L5. And what am I going to divide by? Remember, I said we need to keep track of n. How many values we had? There were 6, right?
6, right.
So we're going to take the sum of L5 and divide it by 6 minus 1, which is 5. All right. So what I'm going to do now is I'm going to go back to the calculator here. And I want the sum of L5. Now there's a couple things I could do. Okay. There's a couple of ways I could go about this, but L5 is what I'm interested in. So probably the easiest one is to go to stat, go to calc, and use one var stats this time, because you're only working with one list of numbers. One var stats, enter, and make sure you enter not L1, okay? You want to enter L5. You want to enter those the sum of those products. So I'm going to change this to L5. Second, number 5, we don't have a frequency list, and I like to calculate that. And I don't care about anything else on here except, now in this case, I don't want the mean. I want the sum. I want the sum of this. So I want the second thing on my list, which is negative 35.4. It's what I have on my list.
I got the same thing, yeah.
And if you take that and it tells you n is 6, okay, now I can say that if I want to find my covariance, let me write it over here. My covariance is going to be, because now I know that my my total was negative 35.4, and I'm going to divide it by 6, the number of values I have minus 1, right? So that's my calculation right here. And then I can just do that calculation down here. So negative 35.4, or I could if I was, if I was actually using the keyboard, the calculator keyboard instead of the cursor, which I'm not, because there I go. So this is negative, and here when you use the negative, use the toggle minus because it's a negative number. So negative 35.4 divided by 5, not by 6. Okay, and that comes out to negative 7.08.
Mhm.
So this covariance here is negative 7.08. Okay, so it's a lot of, it's not hard, it's just time consuming.
Okay.
And
If you-
it's,
With this one, Shauna, if you were taking an exam, would you focus more on me trying to learn it with the calculator or by hand?
it just depends. Oh God, no, I wouldn't do it by hand.
Okay.
I mean, she would probably want to see maybe the first calculation by hand. There's too many I mean, you'd spend half an hour doing all this.
My understanding is going to be a multiple choice.
Then yeah, by all means, use the calculator.
Okay. Thank you,
Like,
Shauna.
don't yeah. Because if you do all this by hand, and oh no, I feel bad.
There's a lot of room for mistakes, right?
That and that's a lot of numbers.
Yeah.
Subtract, add everything, multiply everything together, then add it up again, then divide it by, oh gee, would you, that could be like, you know what you could do if you wanted to, you give like a basic math class, like 5 columns of numbers for the final, and say, here, first take the numbers in this column, subtract the numbers in this column. Then take the numbers in this column, subtract the numbers in this column. Now multiply the results you got in the 2 columns. Then add up the result. Get the sum of that result. And when you're done, divide it by 1 less than the number of values you have in that column. It's all arithmetic. It can be done, but I mean, that would be the final exam.
It's remembering the steps in that order, right, Shauna?
Well, the formula's there. The formula, if you need me to help you to interpret the formula, I can do that. But it's all in the formula, and
Okay.
it's all order of operations. It's
Okay.
the thing about this part of descriptive statistics is that it is all in the formula. Now let me see if she actually helped you and gave you that or not. Because she's pretty thorough. Let me just scroll down and see. Okay, we did that. I'm going to come back to the, okay, yeah. So she did, here's my covariance right here. Okay. There's my slide. This is slide 39.
Okay.
And there's her calculation, right? Now, that's the covariance. All right. Now the correlation coefficient R, or what Blumen calls the Pearson correlation. Blumen will call the sample correlation coefficient the Pearson correlation.
Pearson correlation?
Pearson correlation. Yeah, he was a statistician guy. Oh, and she gives you, see, we should have looked at this because she told us how to calculate it. Look it. Click the data tab, click data analysis, choose descriptive statistics, select labels, find the output range, and then you just click. So it'll give you apparently it'll give you that.
We'll look at the end of the PowerPoints for next time, Shauna.
I mean, I know it'll give you the range and all that, but apparently it'll give you the covariance.
Okay.
If you select it. But the difference between now, remember that she wrote down the standard deviations at the beginning. So if you're getting R and you've done all this work to get the covariance, right, which is the top part, it's the covariance divided by the product of the 2 standard deviations right here. So these 2 standard deviations are the same standard deviations that you wrote from the calculator initially. So to get your final result, you get this covariance here, and you divide by the product of these two to get R. Okay. But that's how it's calculated.
Okay.
All right. And that's the end of that part.
Thank you, my friend.
Does that help a little bit more?
Oh yeah.
Do you
Yeah.
want to go through you want to start going through the other part?
I know we're over time, Shauna. I'll just whenever you're ready to call it a day.
Well, I figured I'd give you a couple of hours today. So we have about 30 minutes left if you want to take it.
Okay. Yeah. Of course, I'll take it. Thank you. Let me just run to the bathroom real quick.
Yeah, no problem.
While you
No
open up
problem.
the
Let
next
me
one.
open up the other slides and you come back. Be comfortable. Up here. Let me just get rid of this. Oops, that's not the right screen. Let me go back to this.
Okay, my friend, I'm back.
You're back. Are you?
Uh-huh.
That was quick. You must be excited about statistics today.
Oh, I got my bathroom close by. I got everything set for us.
All right, my friend. All right, so now this is chapter 4. Whoops, wrong screen. This is chapter 4 that we're doing here. And I'm going to share this screen here. All right, so let's see what chapter 4 is about. Okay, we're talking about probabilities. Now this might take a couple of sessions depending on how, because probability rules are complicated. They don't start out complicated, but it builds on itself and these get tricky. All right.
Okay.
Probability is different than the other chapters because the other chapters are statistics. Remember, probability looks at livelihoods. So we're going to start with experiments and counting rules and how you assign probabilities to things. And then we're going to talk about events and their probability, and then some of the formulas that we have. Okay. And all right. So probability and statistics are related areas of mathematics, which concern themselves with analyzing the relative frequency of events, how often things occur. Probability deals with the likelihood of predicting future events. So probability, you're making a prediction, right? And statistics analyzes the frequency of past events. So statistics is looking at stuff that already happened and analyzing that. Probability looks forward and predicts likelihood.
Okay.
Okay. That's actually a really good way of putting it. I hadn't heard that, but that's actually really good. Let's trace the thought process of a probabilist and a statistician. So, okay, first of all, I have to ask this, forgive me, I'm not trying to insult your intelligence, but I have a lot of students. Do you know what craps is?
Oh yeah, the game in Vegas, the dice.
It's a dice game, right? I have a lot of students and we get problems about craps and they're like, I don't know what that is. It's a dice game that's based on usually with 2 dice, and it's based on the sum that you throw, whether you win or lose or throw again. So a probabilist, somebody who's looking at the probabilities, remember, probabilists are the ones that predict things, right? Would
Okay.
see the dice and think, 6-sided dice, probably each face of the dice is likely to lie face up. So he's thinking about if it's a fair die, right? Then each face, each side is equally likely to occur. Now, assuming he's making an assumption here that each face comes up with a probability of 1/6, I can find out what my chances of losing out, crapping out would be, right? A statistician would see the dice and think, those dice may look okay, but how do I know they're not loaded? I'll watch a while and keep track of how often each number comes up. And then I can decide if my observations are consistent with whether the dice are fair or not. And then if that's true, then I'll call a probabilist and ask them to teach me how to play the game if I think my odds are okay. So this is just kind of the thought process and the difference between it. Kind of a nice way to see it. Probably not going to be on your exam, but definitely helpful to your understanding, I think. And then here, this is talking about some people that we've seen. This is a couple of mathematicians, Fermat on top and Blaise Pascal below, and different ways that probability is employed in different sciences. And in your case, we're talking about things like uncertainty. So managers often base their decisions on an analysis of uncertainty. What are the chances? What is the probability that sales will decrease if we increase prices, right? Mm-hmm. What is the likelihood? How assured are we that the method will increase probability or productivity? What are the odds that a new investment will be profitable? All of these things, they're slightly different, okay? Mm-hmm. This is slightly different here, but they're all related and they all involve using probabilities. Okay. Chances, likelihood, and odds. Odds are a little bit different than the first two, but they're all related. Now, before you can get to any of that, you have to have what we call a statistical experiment, okay? Now, if you have a science background, sometimes students get tripped up with this. The scientists get a little tripped up with the way statisticians look at the experiment, because this is not a randomized, double-blind, controlled experiment, okay? An experiment is actually performing the action and noting the outcome. So for example, let's just make it really simple. If I'm going to have one die, and I'm going to roll the die and record the number that comes up. Rolling the die once is what we call a trial in the experiment. When I start rolling the dice and recording the outcomes, that's my experiment. Okay. And so you repeat the experiment, you keep rolling the die, and you repeat it in the same way. Statistical experiments are sometimes called random because you get different outcomes. This is different than in science, where you would expect what we call validity, where you repeat the same experiment in the same way under the same conditions, you should get the same result. Not true in statistics. We know that to be true, right? Okay. We have more than one outcome. So just something to be aware of probably less critical for you than some of the other students coming at it from a very scientific point of view.
Oh, okay.
Now, here you have experiment versus outcome versus sample space versus event, okay? An experiment is the process. So rolling the die, the process of rolling the die that leads to an outcome. So I roll a die once and I roll 4. 4 is my outcome. The sample space is the set of all possible outcomes. Okay, so let me show you something here. I'm going to deviate from this for a minute. Let me see. I'm going to go to my PowerPoint and go to 4.1. I think it's still up. Because I'm going to send you these as well.
Okay.
This is like the introduction. This is from Professor Nickdell, but these are the introduction to Blumen's chapter on counting rules and probability. I'm just going to give you a couple of hints. Oops. Come back here, you. There you go. Now I want to share. Where's my Zoom? There it is. I lost my Zoom screen. Okay, yeah. So here's my counting rule. So this has some definitions. These will come in. This will tell you. So a probability experiment, which she's calling an experiment, is a process that leads to well-defined results called outcomes. So when a coin is tossed, that's your experiment. You toss the coin. There are 2 outcomes, heads or tails. When a single die is rolled, rolling the die is the experiment. There are 6 possible outcomes. 1, 2, 3, 4, 5, 6. All right. And here we have a trial. She hasn't mentioned that, but if you see that, a trial means every time you do it once. So you could do it 100 times, you would have 100 trials if you did that. Okay. A sample space is a set of all possible outcomes. Doesn't mean that every time you do it, you're going to get every outcome. But these are all the possible outcomes. So if you toss one coin, you can either have heads or tails. On any single trial, you're either going to have heads or tails. But these are your sample spaces, heads, tails. Rolling one die, 1, 2, 3, 4, 5, 6. Answering a true false question, you either get true or false. Okay. Now, this is the one that when we lay it out, trips students up sometimes. We ask them, okay, what if I flip 2 coins simultaneously? What are my outcomes? Well, most students can identify you'll have 2 heads, you'll have 2 tails, or you'll have 1 tail and 1 head. But there's really 4 outcomes, because heads on the first coin, tails on the second coin is different than tails on the first coin, heads on the second coin.
I see.
So you have to be careful. And sometimes when we describe this, we use different coins. So if you had a quarter and a nickel, right? Heads on the quarter and tails on the nickel is different than tails on the quarter and heads on the nickel, right? Because you had different outcomes. That's why that's there. This is another, she'll probably get to this. I just want to give you some more examples of sample spaces. You're probably going to use, you may not use cards in your class, but this is the sample space for a deck of cards. It's right here. So if you have any card, I'll go through her slides as well, but if you have any card probabilities, your sample space is right here.
Okay.
These are all 52. If you, how familiar are you with a deck? Are you okay?
I'm okay with it.
with the deck, like the suits and the
Yeah.
and the numbers and the ranks and all that. Okay, yeah, just let me know because sometimes students need, here's your sample space for 2 dice. 2 dice. So die 1, 1, 2, 3, 4, 5, 6, die 2, 1, 2, 3, 4, 5, 6. Ordered pair 1, 1, 1, 2, 1, 3. Notice, for example, that, and this goes back to something else. Notice that 1, 2 here is a different outcome than 2, 1 right here. That's why it's listed twice. So there's, this means you rolled 1 on the first die and 2 on the second one. This means you rolled 2 on the first one and 1 on the second one. So if you have 2 dice, there's 36 outcomes. Okay. So this is outcomes. These are the possible outcomes. Now, sometimes I'll ask you about the sum. Sometimes I'll ask you about the product. But if you ever need the basic sample space for 2 dice, it's right here.
Thank you, Shauna.
Okay. All right, let me switch screens. I just wanted to give you a little bit of extra examples. So this is pretty much now Venn diagramming. Blumen doesn't do much Venn diagramming. I'll come back to that if I need to. A Venn diagram, it actually comes from logic, and they are designed to help you diagram sets of outcomes. So I could be talking about the number of outcomes on a die versus pulling a card out of something like that. I could be talking about 2 sets. I could be talking about 1 set, but a Venn diagram is a way to diagram that. So now here's the distinction between the experiment, the outcome, and the event. Okay, because sometimes students get these confused. The experiment is the actual activity that you do. You roll the dice, you pull a card, you flip a coin. That's an experiment. The outcome is what you see from there. So you roll 1 die, you see 4, the outcome is 4, right? The event is rolling a 4. You see that?
Mhm.
Or getting 2 heads or something like that. So this is helping you to distinguish this here, okay? The event is a specific outcome. So she
Okay.
has that here for you. It's actually nicely laid out. Those terms, when you start working with them, they get easier.
Okay, Shauna.
But when you first start doing it, it's a little hard to distinguish those. But when you start seeing the terminology, it's not that bad. Probability is a numerical measure of the likelihood that an event will occur. Okay. Probabilities are always between 0 and 1. Okay. Now, technically, this is a little bit misleading. Okay. I understand why she set this up this way, because in theory, you probably won't have a probability of 0. Okay. But this is not, the event is very unlikely to occur. 0 is the event is impossible to have occurred. You cannot have this event. So for example, it cannot be raining and not raining at the same time, right? I cannot have money in my bank account and be completely bankrupt at the same time. That's impossible. Now here, for example, if I say I'm going to roll a fair die, 1 fair die, and I'm going to roll the number 7, that would be a probability of 0. Okay, 0 means that it's impossible. This chart is misleading. The closer you are to 0, so the smaller you are,
Mhm.
the more close to impossible it is, the less likely it is. But you can have a 0 probability in certain instances, in theory. Okay. In practice, we almost never do, and that's probably why she has it like this. But I want you to know that 0 means impossible. 1 means absolutely certain. So if I said, I'm going to roll a die and I'm going to see a number less than 10, that's absolutely certain if it's a fair die that's 6-sided, right? Okay, now we have 3 kinds of probability, okay? There's classical method. This is all the stuff that we study when we talk about cards and dice, and we do all that, all those classical fractions and all the ones you learned it when you took stats the first time. Okay. You also do it when you roll a die and you say, okay, next time you play a board game and you roll a die, how likely is it that I'm going to roll a 4 right now? 1 out of 6. That's classical probability.
Okay.
Relative frequency probability is, I want to find out if these dice are loaded. So I'm going to roll the die 100 times. I'm going to actually do the experiment, right? I'm going to do this experiment and I'm going to roll the die and calculate the data and see what the probabilities are and see if they agree with what I should get, enough for me to understand what the probability actually is. And then there's another method called the subjective method. And the best way to understand this, it's not the only instance of it, but it's probably the best example, is weather forecasts. When you listen to the weather report on the news, and what's his name, her name, Julian, somebody comes on and says, tomorrow there's a 70% chance of rain. What is she basing it on? Yes, she's looking at models. Yes, she's looking at, okay, the storm is swirling out here and it's coming on, but she's able to interpret those models based on an understanding of the data, right? And her subjective judgment, like, it looks like this, but my subjective judgment tells me this. That's a subjective judgment call, weather forecasting. Certain things, like in medicine, certain outcomes for treatments are somewhat subjective sometimes. They can be they're usually based on empirical data, but if you're talking about some new treatment, for example, or some patient with a lot of complicated risk factors, right? Then it might be a little bit of empirical, because it might be based on historical, like historically patients do this well and they recover about this much. But if you've got a patient that's kind of not norm in that way, she's not part of the bell curve necessarily, it might be more about this.
Okay.
Okay. All right. So then she gives you more. Okay, now here she goes into this a little more. So we talked about a fair coin. We talked about the sample space, possible outcomes being heads or tails. And she gives you a little bit of extra stuff about how you write it and what you do. And so here she gives you an example. Now, this is an example of empirical probability. Let's see why. On February 1st, 2003, the Space Shuttle Columbia exploded. This was the second disaster in 123 space missions for NASA. On the basis of this information, what is the probability that a future mission is successfully completed? Okay. So you take the number of successful flights, So you have to read between the lines. There were 123 missions, right? There were 2 that failed. So that means 123 minus 2 is 121, right? There were 121 that succeeded out of 123.
Okay.
Now, is this classical probability? No. Why not? Because classical probability would be based on every outcome being equally likely, for one thing, and they're not. This is not a 50-50 situation where we're 50% certain that we're going to come back and 50% not, or whatever, you know, or 1/123 for each one, right? The other reason that it's not is because this was actually done, remember, that you don't think of this as an experiment, but in terms of probability, think of that. Every mission is either successful or not successful, right? So every mission is an experiment. 121 of them succeeded. There were 123 total, but you actually performed the flights, right? Now, you're not doing it in your little office doing this or watching this. You're looking at historical data, but this counts as empirical probability.
Okay.
Subjective method, okay? So in your case, I talked about the weather. She talks about another example, which is economic conditions. So when economists try to predict when is the next Bitcoin crash and how far will it crash, and how much money will Warren Buffett have when it crashes?
Right.
Okay, how much more money will Warren Buffett have than Brian Seaver or that lady? What's her name? Wood. How much more money will he have than Wood has? That's subjective.
Okay.
Okay, you can read more about that. If you have more questions about that, feel free to ask me because students get tripped up on those, but that's how that works. Then
Okay.
here you have an example of Berkeley oil and the sample space that's given. I think we don't really need to go over that too much. This is another subjective method. So here she summarizes your approaches and where they come from. So it's just kind of a summary of everything that we've talked about. Okay, now the next batch of slides is going to be all about how do you figure out what the probabilities are? How do you figure it out? And that really depends on, I don't want to get too far into this right now.
Okay.
Because this is actually about how you calculate probabilities when experiments are complex. And I have other slides on it for you too, but right now just work on the video and work on trying to take this in, and then but basically where this is going is she's going to talk to you about the counting rules and permutations and combinations, which she's going to spend some time on. Now, notice, I want to show you one thing here, because I would have put this further up in the slide deck personally, when she was talking about probability, okay? I would have put this up there. This is one of the basic requirements. There are 3, but the probability assigned to each experiment must be between 0 and 1. Inclusively, she told you that. Remember, she gave you the chart between 0 and 1, and I told you it was misleading when she said 0 was almost impossible, right? 0 is impossible. 1 is completely certain, okay?
What page are you on, Shauna?
That is slide number, hold on. I need to stop sharing so I can see which slide this is. Let me download it and see. Let me look at the file. Yeah, I think it's, let me check. The slides are really big. Let me see which slide this is. 20, let's see. Is it listed? Oh my goodness. Okay, that is slide number 33.
Oh,
33,
got it.
34, and 35.
Okay.
But 33 is where you should. So the other one that I wanted to make you aware of is that the sum of all the probabilities in a sample space
Mhm.
has to equal 1. Okay.
Okay.
And I would have put that, that's not till slide 34. But I would have put that back up where she was defining probability. It would have made things easier for you.
Okay.
The rest of the slide deck, the second half of chapter 4, is about different ways to calculate probability based on, and it looks like she's focusing on permutations and combinations. I want to take a little more of a look at it because there's a lot of rules that she doesn't seem to be using yet, but I have to see what else is going on, but that should be more than enough
Thank you, my friend.
to get you going. All right.
Yeah. Oh, yeah.
And then I will later on today, after Irma's appointment, Irma's gonna see me this afternoon after lunch. After Irma's appointment, I'm gonna be sending out an email with my schedule for this week because it's all
Okay.
it's different. Like I have some personal things that I have to take care of just about every day this week. So it doesn't really affect like the appointments as much as it does some of the availability. Like I might not be able to answer you quite as much. So I
Okay.
just want people to know that you have some spaces, but like Monday night might be tricky and Tuesday night might be tricky.
Don't worry,
Like
Shauna.
before. So just heads up there in case you were thinking of.
No,
But
my
I mean,
homeworks are done, and I will be on campus this week coming up.
well, good luck.
Mhm.
Stay safe,
Thank you, Shauna.
mask up, and watch out for the other people. I mean, it's just not, it's not even if people are responsible, it's tricky right now.
Mhm. Yeah. Yeah. I hear you. I hear you, Shauna.
So you keep me posted, okay?
I will, Shauna. Thank you.
Alrighty, you're welcome. And
Thanks for
let me know
spending.
if you need a schedule change, because I know you're gonna be going back, so let me know if that means we have to adjust some of your time frames, or if your class is ending up adjusting theirs.
Okay, Shauna. I'll do
All
that.
right,
I'll keep in touch.
Clyde, take care now.
Thanks, my friend.
And as
Bye.
soon as this thing renders, then I will send it to you. All right.
Shauna, you said watch the video, so watch the video that we just did, or
Well, you can watch the video from yesterday. If
okay.
you need help with what I told you is you can watch the video from yesterday if you need help on the stuff with the box plot. But you can also, when this renders, which I'm gonna try and make sure that it renders and send it to you, babe, maybe like by 6 tonight, if it's rendered and uploaded by then.
Shauna,
Um,
if I want to do some of the problems from the Blumen from the summary, the end of chapter stuff, yeah, do you have will you be able to check on your end?
yes,
Oh,
yes.
okay. Thanks,
So
Shauna.
just let me know and send it to me and I'll look at it.
That's great.
Yeah, not a
Thank you.
problem.
Thanks, Shauna. Have a good
You're
day. Have a
welcome.
great day.
You too. Be safe and drink some nice jasmine tea for me. All right.
All right, Shauna. I'll do that.
Bye.
Bye.